Welcome to example number 9. We have a tube that's open only at one end. A certain harmonic is produced when the tube has a frequency of 450 hertz. So we'll just write that over here, 450 hertz. This is some frequency we don't know, so we'll just call that F sub n for the nth harmonic. And then we're told that the next higher one is 750 hertz. So that this is going to be a different frequency, and I'll just label that in a minute here after we talk a bit about it. We also know that the speed of the sound wave is 343 meters per second, and we're asked to figure out what is n equal to and what is the length of this tube. So let's try to sort of visualize this. We really have a tube here that is basically closed at this end, right, and then open here. And we don't know what harmonic it is. And you got to review what happens with a situation where you have the tube that is open only at one end and closed at the other end. What kind of harmonics do you get? The common mistake that people might make is if this is the F sub n for one end open, they might say this is F sub n plus 1. That's only true if it was open at both ends or for a string. But when it's open at one end only, you may recall that you only get odd harmonics. Go back to your notes and review that for a minute. You see over here on the left side, you have open at both ends, and so as you blow into this pipe, there's an opening here, and you get two antinodes, and you get the first harmonic, then the second, and then, of course, you get the third, and the fourth, and the fifth, and it goes onwards. But with one end open, blowing in here, and then this end is closed, where you have to have a node there, then there's only really one opening for the sound to emanate from, and this is loud here, so there's an antinode and a node, and you start off with a quarter of a wavelength, or the first harmonic. And then you jump to the next one, which is not the second, it's the third. And then the next one is after that is the fifth. So you don't have any of the even harmonics, you only get the odd harmonics. So you go from F sub n to F sub n plus 2 to F sub n plus 4, and so forth. So if the first one that we're told, we're not sure if it's the first one, but if this nth harmonic is 450 hertz, then we know the next consecutive one, the next higher one, since it's odd only, so we get only odd harmonics, right? When we go to the, say the first, then we have to go to the third, it's going to be n plus 2. Okay, so next thing is we're going to use these two frequencies to kind of figure out some information about the first, hopefully. You may recall that any nth harmonic is a multiple of the fundamental. So n is the harmonic number, and this is the fundamental frequency. So if you have Fn plus 2, then you would really have n plus 2 brackets times the fundamental. So therefore, if you were to subtract these two, right, what do you get? Well, you get n plus 2 brackets times f sub 1 minus n times f sub 1. And if you work this all through here, you're going to end up with basically twice the fundamental. So the difference between these two harmonics is equal to twice the fundamental frequency. So 750 hertz minus 450 hertz will give you the twice the fundamental frequency. So 300 hertz. It will really give you the second harmonic, which is, we don't get that in a closed at one end situation. So now we know the fundamental is 300 hertz divided by 2. That's 150 hertz. So now if you know the fundamental is 150 hertz, this is definitely not 150. So we need to figure out what the nth harmonic is. So if we were to divide f sub n divided by the fundamental, what do you get? Well, if you divide f sub n divided by n, you're going to get the nth harmonic. You're going to get what our harmonic level this is. So we're going to take 450 hertz and divide it by 150 hertz, and we see that n equals 3. Aha! We solved part A. That's the third harmonic that was given. So this is the third harmonic, and guess what this has to be? That's got to be the fifth harmonic. You can check that out. Take 750 and divide it by 150. You're going to find out that's Fn is equal to 5. Okay, now we move on to part B. What is the length of this tube? So what is L in here? So we'll call that L here. Now L is remaining the same. So you can use either configuration. You can use first, third, fifth, whatever you want. I'll just use the 450 hertz. You see, we know the frequency, right? We know the speed. And we know that from the wave equation, speed equals frequency times wavelength. That means that we could figure out the wavelength. So if we use the third harmonic, then we'll be finding the wavelength for the third harmonic. So the wavelength for the third harmonic would be the speed divided by the frequency. So this would be 343 meters per second divided by the third harmonic frequency, which is 450 hertz. This will then give you a wavelength of 0.762 meters. But is that the length of this pipe? No, because remember, this is the third harmonic. So you kind of have to draw out the picture to show how many waves fit into that length. This is the displacement pattern for one end open with just the first harmonic, and this is now the third harmonic, and this is the fifth harmonic. So we've got this situation. So I would draw that pattern in your picture so that you can realize that the length L represents 3/4 of a wave. So let's erase this little picture here for a moment. And remember that we have to have a node here because it's closed. And there must be an antinode because that's where the sounds emanating out here are very loud. And we're not just going to like a first harmonic, we're going to the second harmonic. So that means that we're going to have a node as well somewhere in here too. So it looks something like this. You have, well, you'll have an antinode over here, sorry. An antinode here, and then a node here, and then another antinode there. All right, and so hopefully you'll see that this length here is equal to 3/4 of a wave. So thus, the length L is equal to 3/4 of the wavelength that we just found out, wavelength 3. So we'll have 3/4 of 0.762 meters. And this will give you an answer of 0.572 meters. Okay. Now, a little side note. Could we have used, say, 750 hertz and solved this problem? Sure you can. Try it out. You'll get a different wavelength, 0.457 meters, than what you had earlier. It's got to be shorter because you got to fit in more waves in here now. And multiply now by 5/4 of the wavelength, you get 0.572 meters. Same answer. It's just that the higher frequency wave had a shorter wavelength, but still the same length of the air column. All right, that's it for this example.